All right, check it out. Look at the bottom quarter of this can. It looks like the aluminum is gone. It looks like the water is there and it's somehow being held back by some kind of magical force field. Is it? Well, the first thing I did was take some sandpaper and I rubbed the paint off of the can. Then I took a stirring rod and just put it over the top. I immersed the can with the stirring rod in a beaker. I then placed 6 molar. Now that may not mean anything to you, but that's pretty dangerous stuff. 6 molar hydrochloric acid into the beaker. And immediately you can see some bubbles coming out. Bubbles, 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 bubbles. Lots and lots of bubbles. What are the bubbles? You're about to find out. So I'm going to speed things up so that you can see it happening. Every once in a while you'll see me lift up the can to see if it's ready. No. Wow, lots and lots of bubbles. Bubbles of what? Why am I doing this in the fume hood? What is my concern? All questions that will be answered. Bubbles, bubbles, bubbles. Lots and lots of bubbles. What I'm looking for is that beautiful look where you see the water inside, but that's it. I'm getting close. I think I've got it. So now all I'm going to do is get rid of the hydrochloric acid and now bring back some water. This is just plain old water. And you can see where it looks like the bottom quarter of that can is gone, and what looks like some kind of film is keeping the water that was already inside the can from coming out.
Okay, so what exactly is going on here? This is actually a simple chemistry demonstration, but there's a little twist to this. What people do not realize when they're drinking their Cokes is that every Coke can has a very thin layer of plastic that is injected in them. That plastic usually comes in as a liquid coating and then it solidifies. So every Coke can you've ever had has had a plastic coating. Now, why is that? Well, if you go to our activity series, you'll notice that you have aluminum up here, and then hydrogen is somewhere down here. Every one of your Cokes or Pops or soft drinks, whatever you're going to call it, have 2 ingredients that are very dangerous for aluminum cans. One of them is phosphoric acid, and of course carbonic acid. Each will contribute hydrogen ions. So what happens when aluminum comes in contact with, let's say, phosphoric acid? This appears to be a single replacement reaction. Yes, yes, yes. Can aluminum replace hydrogen? Yep, aluminum is above hydrogen on the activity series. So what you get is an aqueous solution of AlPO4 and hydrogen gas. Ooh, hydrogen gas. So what could happen if the aluminum is in direct contact with an acid of any kind, in this case phosphoric acid? Well, the aluminum would dissolve into its ion form and then hydrogen gas is produced. For various reasons, that would be a very bad thing to happen, because given enough time, the aluminum can would deteriorate to the point where it would just basically collapse and holes would appear in it. Not only that, but even if you were to get the aluminum can, if you were to get the soft drink in time before the aluminum can disintegrates, it would taste kind of, well, it would taste metallic-y because you would have a lot of aluminum ions in the water. Enough aluminum ions and you could poison yourself. So, before they fill it up with whatever soft drink you want to drink, there is a thin film of plastic that is covering the inside of every can you've ever drank from. That plastic prevents the aluminum from coming in contact with the acid that is found in your soft drinks. So, how did I do this experiment? Well, I got the Coke can and I took sandpaper and I sanded off the paint that was on the surface. Why? Because the paint could very well protect the aluminum from what I wanted to expose it to, which was very concentrated hydrochloric acid. So wherever there was paint, the hydrochloric acid could not affect the aluminum. But wherever the paint was gone, there the aluminum was able to replace the hydrogen, and that's why you saw all these bubbles coming out. I mean, it's pretty aggressive, all those bubbles that were coming out in the video. So that was hydrogen gas. Probably would have been a very bad idea for me to have brought a flame into this because it could have ignited the hydrogen that was above it. Remember that hydrogen plus oxygen is a synthesis reaction that gives us water. So that's why I did it in the fume hood. I wanted the hydrogen to just go away. I didn't want it to linger because given enough oxygen, you have a potential for an explosion. So, yeah, once the aluminum is completely dissolved, then you have the aluminum bottom, which still had the coating on it that protected it from the hydrochloric acid. You had the aluminum top that had paint on it that protected it from the hydrochloric acid. And here you can see the plastic coating that is keeping the water from coming out. So that's how, that's what you're seeing. You're seeing the plastic coat. Just if you were to take a finger to it and just poke it, that would probably be enough to break it, and then water would just come streaming out. So that is the secret of the disintegrating aluminum can demonstration. It is a single replacement reaction. So let's just balance it, just for fun. One aluminum, 3. Okay, looks like we're gonna have to do this in order to even out the hydrogens, and that means you have 2 phosphates, 2 aluminum. So 2, 2, 2, and 3. That is what's going on in this demonstration.